And this is exactly what I experience in my, own lectures to my students. Um, so yeah, thanks a lot for inviting me here, for me to have an opportunity to talk about my research that I do in Eindhoven University of Technology. So the main topic here is integrated nanophotonics and its co-integration with electronics. So I hope through this, overview introduction, you know better what we do, and maybe we can sparkle some collaborations. First of all, at our university, we have a cluster of photonics research groups. As you can see, mainly eight of them, and we form a so-called Hendrik Casimir Institute. Maybe you know this guy if you work in the quantum physics. He's a quite famous Dutch physicist on quantum information. And from these names, you see that we are trying to cover a broad range of research topics from nanomaterials, physics of nanostructures, and through to devices like photonic integration, where I am in, and also electronic integrated circuits, then through to applications, biosensing, and also communication. And within our university, we have a in-house fabrication facility where we make chips ourselves. 800 square meter 3.5 clean room, and within which we can do the whole, supply chain from epitaxy of the crystals, mainly 3.5 indium phosphide gallium arsenide materials, and to all the processing, and finally we can conduct a full process flow to make photonic chips. So for this talk, I mainly split into three parts. First of all, I would like to introduce a little bit of what is photonic integration, and especially what is indium phosphide photonic integration that we do. And then I will talk about the scaling of the PICs in terms of density and power efficiency, and by the use of what we call membrane photonics. And then finally, I will introduce our recent efforts in merging the technology with electronics. And as you can see from the title, it's not a very smooth path, but we learned a lot. So first of all, on the left side, you see, the typical optical elements you see, and you can buy easily from the market. Stand-alone discrete components, optical filters, diode laser detectors, or also something like tabletop interferometers. The idea of photonic integration is to integrate all these functionalities on a single semiconductor chip, like you see, the chip we fabricate in-house in our university. We are trying to shrink, a tabletop sized optical system into a chip on the size of just a few millimeter square. And what we can benefit, first of all, compactness. We can shrink the form factor of your optical system by orders of a magnitude. And they are very beneficial for some complex systems. And also by integrating all the components in a semiconductor chip, then you kind of reduce the need or eliminate the need of mechanical alignment of lenses, mirrors, etc. So you reduce the complexity of assembly, and then it can lead to a significant reduction in the cost of making these optical systems. And finally, the semiconductor industry is booming, and powered by the semiconductor manufacturing capability, there's also opportunity to scale up in volume. So we're not talking about building one system a day, but we are talking about millions of chips per hour. Yeah. Why do we choose indium phosphide? Because this compound is kind of a a selling point or the very unique recognition of our university. We choose this because of two wavelengths. I was told I need to point here. Does it work? Oh, yeah. So because of very important two wavelength bands, as I indicated here, 1310 nanometer, which we call the O band, 1550 nanometer, C band. They are the most important wavelength for optical communication. Yeah, 1550 nanometer is more used for long haul transmission. So for example, sending signal from Vilnius to New York, then you need this wavelength. For 1310 nanometer, it's more used for relatively shorter distance. So imagine a Facebook data center. Where are the signals? How are the signals transported? In optics and using this wavelength. And indium phosphide plays a role here because, as you can see in this diagram of lattice constants versus the band gap, I draw a straight line from indium phosphide down to the cross section between gallium arsenide and indium phosphide, this line. So it means, and at this intersection, we have a ternary compound, indium gallium arsenide, which is a lower band gap, but the same lattice constant, so we can achieve a lattice matching. And then the more interesting thing is the red line between indium phosphide and the indium gallium arsenide, because then on this straight line, you can have quaternary material, indium gallium arsenide phosphide, where you can always maintain the lattice matching while having a flexible bandgap tunability. Yeah, and it covers both the O band and the C band wavelength. So that's why indium phosphide has becoming so interesting, originating from the optical communications. So the bandgap tunability starts from the intrinsic bandgap of indium phosphide, which corresponds to about 1 micrometer of wavelength, and then slightly longer is the quaternary material containing indium gallium arsenide phosphide or aluminum containing compounds, which covers the typical near infrared. And we can also achieve a slightly longer wavelength up to 2 or 2.1 micrometer by adding antimony into it. Now I talk about the integration philosophy. So how to create a complex optical system just in a single chip. You need to have a technology to integrate all the necessary optical functions into a same chip. So in this cross section, you see that on the same. I don't know where I am pointing. You can see that on the same indium phosphide substrate, we can build a complex layer stack, which contain typical anode, cathode, or an active region to form a proper laser diode, which is shown on the left side. And then in the middle, we can we have a technology to remove the red part, which is the active medium, to make it a passive waveguide, deep, shallow, different optical properties. And in the slightly right side, we start to bias this passive waveguide diodes to benefit from electro-optical effects. So we can have a phase modulator. So we can also manipulate the phase of the light. And then on the right side, you see a very special triangle-based waveguide to manipulate the polarization. So it's very similar to the electronic integration. On our chip, we can also have all the functionality on a single chip, from amplification, phase control, polarization control, and then to the waveguide. So if you see the diagram on the left, you see it's almost a one-to-one match to the philosophy of CMOS or electronic integration, right? And on the bottom side, you see a typical example of these building blocks fabricated. So by having these fundamental functions or building blocks, you can start to play around it to build a system. We call it a Lego game. So it's like every building block is standardized, right? And then a kid can do the plug and play and build, I don't know, a dinosaur or roller coaster. Similar here. You see that I give you a few examples by combining, passive components, optical splitter, then um, with a waveguide, you can have a ring resonator, wavelength multiplexer, then adding phase control, you can have a optical filters or photonic delay lines. Then adding active components with the red building block, you can start to make lasers, right? If you put a amplifier in between two mirrors, you have an on-chip laser. If you put them into an array connected to a wavelength multiplexer, you have a multi-wavelength laser, which can, emit different lasing wavelengths at the same time, etc., etc. Yeah. And by playing this, we can cover, a wide range of applications. I just give you a screenshot of what we have done in the past. Our group has designed, I don't know, more than 500 different chips in the past years, and covering from, typical optical transceivers, the laser transmitters for WDM system for communication, and in the middle, it's actually my PhD work, a tunable laser for OCT, optical coherence tomography for healthcare, and also some transmitters for microwaves, and also some chips which can, can operate at a very high speed to bridge optics and a microwave or even terahertz waves. And we are also, looking into beyond indium phosphide, because indium phosphide is great at many things, but in terms of there's no the point is there's no one single material system which is perfect at everything. Yeah? Indium phosphide is very efficient in light generation, detection, etc. But there are other materials like silicon nitride, which can do better in kind of wave guiding and other things. So we are also trying to combine different material systems. So that's why we have a technology called indium phosphide membrane on silicon, trying to combine different materials. I will elaborate this later. And we are also working on micro transfer printing or wafer bonding to achieve this. Just a few example of the recent new chips that we have made. This is a recent laser chip that we developed, which it's a tunable laser, completely integrated in a 5 by 5 square millimeter chip size, and it can achieve about 100 nanometer continuous tuning. So it was one of the records. And in the middle, you see a highly densely integrated optical modulator, which can be modulated beyond 100 gigahertz. And we are also trying to integrate new materials, like we integrate, as you can see here, a cerium doped Yuqin material, which is a magneto-optic material, onto our waveguide, so we can actually create optical isolators on chip. And we work with European partners and industry to cover, using our PIC technology to cover different applications, from the more traditional telecom, datacom for data centers, through to actually structural sensing for windmill, turbo, and airplane. Then recently through to optical sensing for agri-food, for metrology, and for healthcare. And just as an example, we recently have a EU project called Spike Pro. It's led by one of my colleagues. It's trying to bridge the world of photonic neuromorphic computing and electronics. You know that many of the signals we receive, especially from the computers, they are electrical signals. but there is a lot of advantage, doing computation in photonics domain. Why? Because we can do parallelization. Yeah, photons has property not only intensity but also phase, polarization, modes, etc. So we can actually stack multiple channels in one physical chip. So this project tries to create an interface between the two. So, for example, a typical, electronic neuron is people use a resonant tunneling diode, which is an electronic diode device. But then we try to create a technology that it can be integrated with a semiconductor laser. So the signal received by the resonant tunneling diode can be transmitted seamlessly to an on-chip laser, where the laser converts the electrical pulse to an optical pulse. Yeah? Then you can utilize the optical pulse for further processing. And we are also working with some partners in Italy to create PICs for quantum applications. Yeah, why people use indium phosphide technology? Because we can create quantum dots which can emit single photons using indium phosphide quantum dots, and also we can create very low loss and low voltage optical modulators for sideband generation, and also indium phosphide is also quite good at creating single photon avalanche diodes. And everything are waveguide coupled. It means you can create a complete waveguide systems on a single chip. So I move to my next topic, scaling. Because I showed you a few examples of the chips we made in the past, and they are mostly the red dots here. Red dots represent the chips made of indium phosphide. And I plot here over the years how these chips scale up in terms of component counts. And you see that it's growing kind of exponentially, but in a relatively slow pace, right? And then there's, in the recent maybe 10 years, there's the blue dots, which is silicon photonics. Maybe you must have heard of it. They ramp up at a much faster rate, yeah? You see that while indium phosphide, the component count saturates around few hundreds. The component count for silicon photonic chips, especially for MEMS switch or optical phase array for LiDAR, these chips, they scale up at about 2 to 3 orders of magnitude. This sounds very, very exciting, right? But if we look at a complete system, this is where these circles are. There are only very few demonstrations on a complete active passive chip on silicon, because all the world record high component count chips on the top side, they are all passive silicon. And when people start to integrate optical amplifiers or optical modulators, which are active components, they are within the red circle. Yeah, one by UCSB, one by Intel. And you can see that the component count is not too different from that of native indium phosphide, right? So this is where the bottleneck is. So the scaling of the peaks or the scaling of the density, it seems it cannot be solved solely by silicon photonics, because once you add active functionality, you are on the same line with the indium phosphide. So it's reasonable to think that active components, yeah, the amplifiers, modulators, they are the bottleneck for the future scaling of the chips. And it can be seen even clearer from this graph. So we tried to decompose and plot, what kind of components people use in each of the chips, and we plot them into this graph. So you can see that in the past years, in the very recent years, it is the passive silicon components and the MEMS and also thermal optic components which are really shooting high in component count in density. Yeah, well, if you wanted to use electro-optic components and optical gain, you're still there. It has been, you see a flat top effect, right? So it means the technology has not scaled for over 10 or 15 years. So actually, this is the bottleneck we identify, and this is the bottleneck that we try to tackle with. Yeah. So the choice of technology we use is to try to shrink the indium phosphide technology into a much smaller form factor. Yeah, if you see on the left side, this is a illustration of a conventional indium phosphide laser structure or waveguide structure, where you grow your entire diode or waveguide structure on an indium phosphide substrate. Yeah, because you are creating a relatively weak optical confinement, because the index contrast is very, very small, it ends up to a very large laser diode, typically 2 to 6 micrometers in width. And what we're trying to do is to shrink the entire diode structure into a much smaller cross-section. As you can see on the middle side, we try to separate the waveguide, indium phosphide waveguide, apart from the substrate, so that it can have a much higher index contrast, leading to sub-micrometer dimensions. Yeah. So in terms of waveguide, it's very similar to the silicon photonics, but it's made of indium phosphide. On the right, you can see a typical mode profile. Yeah, and you can see that the optical mode is actually very tightly confined in these indium phosphide waveguides. And also, as I already gave a hint here, because now my optical system is independent of the substrate, so I can actually integrate this system onto any substrate I want. For example, a electronics substrate, right? So it can also potentially enable an integration with electronics at wafer scale. So we went on this path, and this is what we have now. We can do in-house fabrication of this, indium phosphide membrane integrated on silicon at the wafer scale. So we use 100 millimeter wafer size, and on this indium phosphide membrane, we can create laser cavity and also all other kinds of nanophotonic devices, micro ring resonators, photonic crystals, and also even plasmonics. What you can see here is a coupling region between a plasmonic waveguide and a conventional indium phosphide waveguide. First thing first, the reason we use indium phosphide to membrane structure is not only because of its high index contrast, but also we chose indium phosphide because it can give us native lasers. So we designed, on top of this membrane waveguide, as you can see here, a laser structure, a very compact laser structure. It's S-shaped, so the P and N contacts are on the two sides. And it utilizes as you can see, a very short and efficient coupling to couple from the active side to the passive. And because now we are not coupling between indium phosphide and silicon, we are coupling between indium phosphide and indium phosphide. So the mode matching is very good. So it leads to a very compact taper structure of only 20 micrometer or so. And because it's the same material system, so we can process it in the same process flow. It means the taper structure can be aligned very accurately with the passive waveguide because it's done by lithography. So this is the example of the amplifier we created on this very thin optical membrane. About 200 dB per centimeter gain we can achieve in a full quantum well system, which is very comparable with the conventional indium phosphide devices. But the thing, the point I want to raise here is a universal challenge. So it's the optical amplifiers are intrinsically very poor in efficiency, especially if you want to use this device to amplify a very weak signal. For example, if you start, in an optical communication system, if you start to try to amplify a microwatt level optical signal to milliwatt, you need to pump your amplifier very hard. And then if you calculate the wall plug efficiency, it's less than 1%. So it means if you just buy a conventional amplifier, just use it as is, 99% of the power electricity you pump into are wasted. Where does it go? Heat. Yeah. And it's common for any kind of semiconductor amplifiers. So we are trying to think, hey, since we have a unique platform, can we play with some tricks at circuit design level to try to boost its efficiency? One of the idea we have is if the weak signal, when it passes through the device, it only consumes 1% of the power. It's so low efficiency. Can we kind of recycle the same device for multiple use? So this is the one of the circuit we have created. We call it a loop back circuit. So basically, we want to reuse the same device for multiple times. As you can see, we inject a fundamental mode from the left side into the amplifier. So of course, it will be amplified for the first time. But then we kind of re-injected the same signal, the amplified signal, back into your amplifier. Yeah. And the trick here is before entering the same SOA, we use a mode converter. A design is shown here to convert the fundamental mode into higher order mode. For example, in this case, first order mode. Then it got injected into the same SOA, got amplified for the second time. And the benefit is very obvious because we calculated the power efficiency. In this case, we get 3 times higher power efficiency just by this, additional loopback. And also, you can imagine the benefit is that by, keeping the same, if you want to achieve the same amplification, it means you don't need the original footprint of your SOA. Yeah, you can reduce the footprint. For example, in this case, by reusing the light for one more time, you can halve the footprint of this device. So it's very beneficial for efficiency and for footprint. And also the additional circuit on the left and the right side, they are independent of your SOA technology. Yeah? So this loop-back circuit, in principle, can be applied to any photonic technologies. Then based on this, we try to create lasers. We have a collaboration with KTH to develop, direct modulated lasers for data centers. As you can see, now we can build a very compact laser where the SOA, the amplifier in the laser, is only as short as 100 micrometers. And we also create an external cavity on the right side with on-chip phase tuner, phase shifter, where we can fine-tune the coupling between the main cavity and the extended cavity on the chip. And by doing this, actually, we observe that we can extend the bandwidth of your laser by, several folds. So if you can see on the graph on the right side, we see at around 7 to 8 gigahertz position, we have a resonant peak. And this is the relaxation oscillation of my main laser cavity. Yeah, it's determined by my laser cavity length. And then at around 25 gigahertz, you see that in from the red curve to the green curve, there's a second peak rising up. And we can obtain this second resonance peak just by simply fine-tuning the extended cavity by this on-chip phase shifter. And if you have the right, it's all about the phase matching between the two cavities. And when you have the right phase matching, you have the second peak resonant rising up, and you can extend your laser modulation by, in this case, almost 5 times, right? So we demonstrated 25 gigahertz bandwidth laser modulation, and which can support 40 gigabaud data transmission. Yeah. And also, because we are now integrating our indium phosphide onto a silicon material, so we are actually with also a dielectric, low index dielectric in between. So actually, how to manage heat is very important. So on the left side, you see a laser, typical laser we made, indium phosphide membrane laser on silicon without any, extra care for heat extraction. You see that the power efficiency is as low as a few %, and you see the laser kind of dies out very fast when you pump it harder. But then we created a micro heatsink, as you can see on the same image on the top, connecting the electrodes of the laser through to the bonding layer and reaching the carrier wafer. So it's act as a efficient heat sink for the laser, and you can see we can halve the thermal impedance of those laser structures, and bringing the warp plug efficiency to almost 20%, which is quite substantial. And another benefit is that on this membrane technology, you can create really fast optoelectronic devices. In this case, we designed a uni-traveling carrier photodiode. I just explain a little bit how it works. On the top right, you see a typical diagram of a PIN diode, right? You have an anode cathode with an intrinsic layer in between. And when the light is absorbed, you have electron-hole pair generated, and they need to travel to the side of the diode, right? And if you see the diagram on the right, you see that the limitation here is that electrons travel much faster than the holes. Holes are, heavy. And those holes, their travel time becomes your major bottleneck in these typical photodiodes. So people designed a new device called the unit traveling carrier, UTC, where the absorption region, if you look at the left side, is not in the center anymore. Your absorption region will be slightly p-doped, will become part of the anode. The benefit here is when the light is absorbed, electron-hole pair generated, the hole will stay there because in the anode, the majority of the carrier is already the holes. So the hole actually doesn't need to travel. Only the electrons need to travel. Yeah, and as you see in the diagram on the right, electrons travel 10 times faster than the holes. So this is the way, by a smart diode design, people can bring up the speed of the photodiodes dramatically. So we also designed such a structure on our membrane platform, and you can see that in this cross-section, we have something very unconventional, because we have electrodes and some of the semiconductor structures buried inside my bonding layer. And there's a reason we do this. If I compare our design to a conventional photodiode made on indium phosphide chips. The fundamental difference is that in the conventional design, everything is patterned and processed from the top side of your wafer, right? And it means that your metal has to land on the top surface, and laterally, it has to be placed very far away from your waveguide. So in this case, if the blue rectangle is your detector waveguide, then your metal has to be placed on two sides, which has to be more than 1 micrometer. So, and then the electric current has to pass through this red layer, which is a very thin conductive layer, which has intrinsic resistance, right? And in our design, you can see that the two metal pads are actually flipped on the backside of the diode, and they can be brought much closer to each other. Yeah, because now because we flip the metals on the backside, so the interaction with my modes in the optical waveguide and the metal, they are much reduced because the metal are now placed diagonally to my waveguide. So we can bring the distance of the metal from more than 2 micrometers down to less than 400 nanometers. Yeah. And how do we do this? How do we do this? We do use a unique double-sided processing. It means that we can process the semiconductor wafer before the bonding. For example, we start with an indium phosphide wafer with a complete layer stack. We can do processing from the top side to form some mesostructures and also electrical contacts. Then we can planarize the surface, and then we flip the wafer to bond it onto a silicon substrate. And then you can see here we can remove the indium phosphide substrate, leaving a membrane somewhere here. Oh. And then we have, after removing the indium phosphide substrate, we can achieve again a very flat surface, and then we can do further processing on it. And at this step, you can see that we can create mesostructures and metal structures buried inside my membrane. One benefit, as I mentioned, is that we have, in this case, an extra degree of freedom to design its optical and electrical properties. Especially, it's very beneficial in optimizing the RC constants of the diodes. And then another benefit is that the wafer is now exposed to, it can expose ultra-flat surfaces, one at the beginning. I have to align the dots. One at the beginning here, and the second time after my substrate removal, I can achieve 2 times ultra-flat surfaces, which are extremely important if you want high-resolution lithography. Yeah. So on the bottom right, you see an example of the double-sided processing. You can see that we have a metal flipped on the backside of the membrane and buried inside my bonding layer. So we created such a photodiode using our technique. On the left side, you see the image of the photodiode, and yes, according to our measurement, it can really operate very fast. At 4 volts bias, we can achieve a electro-optic bandwidth beyond 110 gigahertz. Yeah, actually, our latest design can go even slightly better, towards 150-ish gigahertz. So you can already connect optical band to millimeter wave band. And another thing is that such a diode is extremely small, even though it's very efficient. It's only 5 by 2 square micrometers. It's a very tiny bit on your chip, and so and it's waveguide coupled, so it can be used to build very complex, systems on chip, and also we can design on-chip antennas for such devices. And the more exciting is that it's not such a device can be even scaled to higher bandwidth or high efficiency in the future, because we try to uh, um, analyze, the RC constants of these devices. So we, based on our measurement, you see, we calibrate out what are the junction capacitance of such photodiode versus its device area. As you can see, we can achieve a low junction capacitance as low as 4 femtofarad. It's an extremely small value while maintaining a very small series resistance. There are formulas in the textbooks, right? If based on these two values, you can calculate the RC limited bandwidth. And it shows us that actually, potentially, such a device can go beyond 1 terahertz. Yeah, and this is something we are targeting for in the coming years. And on the optical modulation side, we have also did some interesting experiments. Because we created such a slot waveguide, as you can see in the mode profile in the middle, by placing 2 waveguides extremely close to each other, leaving only 100 nanometer each gap. Actually, most of the light intensity is not in the waveguide, but in the slot in between. Yeah, it's not. It's quite commonly known, right? And you can utilize this to create a very efficient optical modulator, because in the gap of this slot, you can fill in efficient electro-optical polymers. Then by applying electrical field, you can modulate the polymer, which has a very strong interaction with the optical mode. Yeah. And we are also motivated to see that how indium phosphide can play better than conventional design in silicon, because indium phosphide, in principle, when they are doped at the same level, they should have a much lower optical loss and much higher electromobility, which are needed for optical modulators. So this is a first device we have fabricated, very nicely defined slot, nano slots filled with optical modulators, and we achieve about 40 gigahertz bandwidth. Our game doesn't stop. We can also play with some exotic stuff. We're inspired by the layer stack of our laser diode structure, because we have a indium phosphide-based cladding, P and N side, and in the middle we have a ternary or quaternary-based active region. By some, selective processing, you can actually remove the center active region and making the top cladding suspending. So then you create a MEMS, or people call it NEMS, right? Nano mechanical system. So this is what we have done. If you see on the right side, we actually, in some areas of the wafer, we dig out the active region selectively, and then we create a top cantilever utilizing the top cladding made of indium phosphide. And then at the bottom, we use the bottom end-doped cladding to form a waveguide. So in total, if you see this cross-section, it's a 4 waveguide coupled nanomechanical structures, right? And another benefit is that because we are creating this mechanical structure from a laser diode, the layers are intrinsically doped, so we can actually actuate this this cantilever by just applying electrical field. Such a system turns out to be extremely efficient. By a 6-volt bias, we can achieve in total of 5 pi phase shift, and within a very compact length of about 150 micrometer length. Yeah, so it can be used for very low energy optical switching or displacement sensors. We are also trying out to see what what kind of complexity we can really demonstrate This is a very recent result that we work with NVIDIA on building optical switch. NVIDIA is really interested in this topic to use light to do a switch, signal switching in the data centers. So we designed an 8 by 8 optical switch chip and also 16 by 16 optical switch chip. And we designed especially a polarization insensitive SOAs to be integrated into this chip technology. As you can see, we have a very high density integration of these SOAs together with other passive components into a single chip. Yeah, this is so far I would say, in terms of active passive integrated chips, this is so far the most complex chip ever reported. And especially on the right side, we integrate almost 300 SOAs in just 10 by 4 square millimeter spot. Yeah, extremely high density. And furthermore, we work with ASML on chip technology, not only because they are just our neighbors, but actually there is a benefit of using the chip technology for next generation ASML machines. So we are not only using the ASML machine to make chips, but we are making chips for ASML machines. Why? Because, like I said, the form factor, the compactness, plays an important role here. So on the left side, I show a diagram of a wafer alignment sensor that ASML use. Yeah, so basically the system is built by this size of box, which contains light source, detectors, and a complex lens system to form a kind of laser diffractometry system. I cannot tell too much about the principle, but the idea here is to replace the entire bulky optical system into a single semiconductor chip. And we have, as you can see on the right side, we have a first demo just coming out last year. We built an entire optical diffractometry system on a single chip, which can actually also emit light out of and back into the chip using a optical free space coupler. We designed it based on a hologram, the principle of a hologram. And the uniqueness of our coupler is that it can cover extremely wide optical bandwidth. It's really demanding because of the company, but we achieved that the single coupler can work across the optical wavelength band of over 300 nanometers. Yeah, and then we coupled these free space couplers with on-chip interferometers to build our first demo of a single chip wafer alignment sensor. And in the lab of ASML, we achieved actually sub-nanometer precision. Yeah, it's one of the it's already comparable to the performance of a bulk optical system. Yeah. Another benefit that we are looking into is actually, again, parallelism. Because by doing on-chip, you can scale up 10, 20 sensors integrated on a single chip, which you can't do by bulk optics, right? Then you can also start thinking of multiplexing technologies, wavelength multiplexing, mode or polarization. You can use multiple degree of freedom in the light to actually potentially make not only a smaller sensor, but also a better sensor. So this is something we are also actively working on. And the final topic, the road to integrate with electronics. And because, like I said, we can create a membrane, kind of a floating or independent of the substrate at a wafer scale, why not put it onto an electronics wafer? If you design your photonic circuits and your electronics driver properly, we call it co-design, you can actually, after the combination, you can have a direct connection between your laser and your electronic driver in a single chip. And so we call it wafer scale assembly. Yeah. So, and it's kind of because we are combining the two things in a 3D scale, so people also call it 3D integration. The major benefit, as I indicated here, is to remove remove the bond wires or bumps which people use typically for chip assembly. Yeah, when you need to assemble, individual photonic chip and electronic chip, you need these bond wires, which are centimeters or millimeters long. And if you talk to experts, they say, well, they have a super high parasitics, which actually will become the bottleneck of your entire system. So in this case, since we do 3D integration, we are bringing the photonics and electronics really, really close, down to several micrometers. So we are shrinking the distance of the interconnect by several orders of magnitude. Yeah? So in principle, we can make a much faster interconnects between the two systems. So this is a wafer. We first trial we ever made in collaboration with NXP. Maybe you know this company. So we actually integrate the entire wafer of indium phosphide membrane, full of lasers and other things, onto a CMOS electronics driver. Yeah. On the right side, you see that we have a zoom-in picture of the wafer surface, and you see electrical pads of two colors, right? You see the pads of silver color, which is actually the pads from the CMOS, the copper aluminum. And then you have the golden pads, which are the gold-based pads on lasers. So they are very well co-designed and aligned, and we can, after the integration, we can do some extra processing to make the final connection. And we call it through polymer vias, because in this integration, we are kind of gluing the photonic wafer with the electronic wafer with an intermediate glue in between. And this is a polymer. So as you can see on the left side, after the integration, we can drill holes, through the polymer, and then expose the electrodes from the photonic side and the electronic side, and then make the connection. And on the right side, we try to characterize, the performance of such vias. This really doesn't work. On the top right, you see that a typical test structure, a transmission line on the CMOS, and the transmission line from the photonic side, and in between, in the blue square is the vias that connects the two. And note that they are not in the same plane. They are 3D. They have an offset in 3D. Yeah. So this wire is going downwards into this screen. So we are we characterize these test structures. Very good electrical performance, no degradation after temperature cycling, and these vias, they can support more than 67 gigahertz RF transmission, yeah, with negligible loss. So this is way beyond the state of the art in chip assembly technology. Of course, like I hinted, it's a bumpy road. To achieve that, there are several, technical challenges we are facing. First of all, I'm not sure how many of you have handled a semiconductor wafer. They're typically shiny, right? Otherwise, something is wrong. Those shiny wafers, they tend to drift with each other when you put them close to each other. And they also tend to trap air in this very thin interface. And in our particular case, they can lead to a relative shift between the two wafers. And our measurement shows that it can drift up to hundreds of micrometers, which is horrible because a laser is 2 micrometer in width, right? Electrical pad may be 100 micrometer. So if you drift that much, you misalign your laser and your IC driver completely. And this is an example. So from the design, we align the electrodes so perfectly. But in reality, as you can see, there's a significant drift between the two wafers. Some people say, yeah, you can repair it by rerouting your metal by some post-processing, right? But there's of course a price to pay, right? By rerouting, you add extra parasitics, and you have to sacrifice chip area for these unnecessary repairments. So how we can solve it? We are thinking, hey, if the wafers drift, can we lock them mechanically? And this is something we created. We call it an invisible anchor to help mechanically lock the wafers. And why we call it invisible? Because after all the treatment, it will become part of the system, and you don't see it really. How do we do it? We first, as you can see, we prepare the two wafers. One can be photonics, one can be electronics. And on one of the wafers, we not only coat the polymer, but we actually pattern the polymer and cure it. So as you see on the bottom one, on the wafer one. So it's a cured, hardened polymer, which are actually very stable. On the other wafer, we don't do it. It's still, a liquid phase polymer coated on the wafer. Then we perform the wafer bonding. And you can imagine that those hardened pillars, they penetrate through the liquid and reach into the surface of the top wafer. And using the friction, we can achieve a mechanical locking. Yeah. And the magic happens when we do a thermal treatment to cure the entire system. And then the bonding interface become an entire, completely hard cured polymer. Yeah. So the anchors we created before becomes part of the bonding interface. And this is the trick we play. And the benefit is enormous, as you can see from, when we bond without anchors, we typically get tens of micrometers misalignment, or even more than 100 micrometer. And then you see the black dots, which is with our anchor system, we can press it down to just a few micrometers. Of course, people say, yeah, there must be some difference between your anchor and the rest of your bonding interface, because, like I've shown here, the anchor structure is actually cured twice. So we try to also analyze whether there might be some mechanical strain induced or optical property change. You do see an interface here, right, between the BCB anchor we created and the regular BCB. And why there's an interface? It's because, yeah, the anchors are cured twice, so it's actually denser. It has a higher density. But in terms of photonic application, we also measured the index change because induced by this treatment. The index increase is actually minor, 0.025. So any waveguide system will not feel it. Yeah, so it's actually very, very convincing results. Yeah. So this is only one bump on the road. I show you another bump. Because we are integrating a complex system now, right? We have indium phosphide materials, we have silicon. Inside indium phosphide silicon, we have metals. Then for the bonding, we have adhesives, which is a polymer. And then somewhere we have also hard dielectrics like silicon oxide, silicon nitride. It's a very complex material system. And every material has a different thermal expansion coefficient. And the consequence is that when you perform the bonding, usually at an elevated temperature, I don't know, 200 degrees Celsius, and then after the bonding, you have to cool it down. You can take the wafer out, cool it down. Then the thermal expansion coefficient kicks in, right? Because every material shrinks at different rates. I show you a worst case scenario when we try to bond indium phosphide onto a glass substrate. which has the highest, difference in this expansion coefficient. And you can see that the indium phosphide membrane indium phosphide is fragile, right? It's so fragile that it cannot overcome the strain built inside the system, and it cracks like pieces. And of course, this is a worst case scenario. But our goal is to quantify what kind of, to quantify how they shrink and how they influence our system. So that leads to the plot on the right. You see the data for indium phosphide. Of course, this is an indium phosphide to indium phosphide bond, the same coefficient, right? So you don't expect the expansion or the strain built inside your system, but you do see a significant value around 300 ppm for silicon and for silicon carbide as a substrate. So it means when the chip is cooled down to room temperature, the thermal expansion coefficient builds in, causing strain and deform the indium phosphide membrane on top, right? So actually the entire membrane experience a linear expansion because of this. And some people may say, yeah, 300 ppm, it's 300 part per million. It's a tiny value, right? But if you, the thing is a scaling, the wafer scale matters because we are talking about 100 millimeter wafer size. If you multiply 100 millimeter by 300 ppm, it is about tens of micrometers. So at some location of your wafer, your originally made structure may jump to another location by tens of micrometers, which you don't really want, right? So that's why this quantification is very important. It means in the future we can compensate it. Yeah, we can only compensate by knowing precisely the value. And it's not a fully fixed problem. Why? Because besides this linear distortion related to the thermal expansion coefficient, we see residual distortion. So we quantify in each spot of the wafer how each spot deforms, right? Or where each spot drifts. And after calibrating out this linear expansion, you see there are nonlinear components remaining. So even though after this linear compensation to this linear coefficient, we still have uncertainty of where each structure go on this wafer. And this is ongoing research because we try to map this, arrows, which is the nonlinear distortion, with the thickness of the layer stack because there are some non-uniformity of the polymer involved. There seems some correlation between where the arrows point to related to the thickness of the polymer. As you can see, in the center, in the red area, seems all the arrows are pointing into it. But then it's also not the case for the other part on the left side. So it's currently not very conclusive, and it's ongoing investigation. Yeah. But I just want to show you that it's a very nice dream, to combine electronics, photonics in a single chip, but it's a very complex problem. But the last one, we are moving forward to a demonstration. We work with a French Institute 3.5 lab, where they produce one of the best-in-class electronics transistor technology. They have a indium phosphide double heterobipolar transistor technology, which can provide cutoff frequency up to 0.5 terahertz, extremely high frequency. And then by using this transistor technology, you can build a laser or modulator driver going beyond 100 gigahertz. Now our goal is, why not take one of their wafers? So on the left side is a wafer produced by them, like fully populated of electronic drivers. Then we do co-design, and we integrate our indium phosphide photonics on top of it. And in this case, I just show you one of the design. We have a ultra-fast photodiode. I just showed you before, 100 gigahertz or beyond. And then you see that this photonic device where am I? Oh, here. Photonic device is here. It's slight offset with your electronic driver with these electrodes in between. These electrodes are designed 3D way because they are connecting two systems in a 3D. Yeah, and this is ongoing results. So hopefully we can achieve something demonstrable in the coming months. We are also, last thing but not least, thinking about scaling of wafer size, and because we are always asked by people, hey, indium phosphide, what's the future for indium phosphide? Indium phosphide, most of the labs do 2 to 3 inch this size, and we are slightly better to 4 inch this size. Industry just moved to 6, but that's about it. 6 inch might be the fundamental limit for indium phosphide material system, just because of the brittleness of the material itself. So we are actually looking at technologies, how to go beyond the wafer size limitation for the indium phosphide. Yeah, I give you 2 examples of the running projects we are working on. With IMEC, we are working on actually microtransfer printing. So we will produce the indium phosphide membrane devices in its source wafer, 3 inch, 4 inch, 6 inch, doesn't matter. But then we can transfer them onto a much larger silicon wafer, 200 millimeter, 300 millimeter, by picking and a place where we can pick small pieces of indium phosphide and populate them onto silicon substrates. And also in another program, we are trying something even more radical. If you know how SOI wafer is made, it's basically bonding of 2 silicon wafers, right? And removing the substrate of one. This was invented by this company, Soitec. But the same principle can be applied to indium phosphide on silicon as well. Why not, bond indium phosphide to silicon wafers and then using they call it smart cut technology to remove the indium phosphide substrates. Then you have a indium phosphide, we call it a seed layer, right on top of your silicon surface. And how does it go beyond the wafer substrate limitation? Simple is that it's same as you do tiling on your bathroom. Okay, you have very large area, but the limited size of your tile. How do? You stack them next to each other, right? Okay, similar concept. But then the nice thing is, once you have a indium phosphide layer populated on silicon, you can start grow laser or any other indium phosphide structures, right? You are using those kind of substrate. Yeah, there are a lot of rooms to play around using this technology. So I'm not going too much detail because I think I'm running over time, but do check our website if you're interested. So as a summary, I hope I have given you an overview of what indium phosphide can do to build complex circuits and systems. And our main research activity is on heterogeneous integration or 3D integration to combine 3-5 material with other optical materials. And then, by combining best-in-class photonic technology and electronics technology, we are really advancing in this chip technology, and it's both academically exciting and industrial high potential. So yes, thank you.
Thank you, Yuqing, for recipes, for roadmap, where to go and what to do. I think that before the second presentation, we still have several minutes for questions. So the time now is open for questions. Yeah, please.
Hi, thank you for your very interesting talk. I have a specific question. So what do you think? What's the future material for the interconnects, or what is the most promising material?
Do you refer to electrical interconnect or optical interconnect?
No, the interface in between. Yeah, so on one side you have a photonics integrated chip, on the other side you have electronics, but in between there must be an interconnect.
Yeah.
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 So what's the most promising material for that?
Metals. If you anything with so the guideline here is electrical conductivity, right? There's one thing. Another thing is compatibility to your process. Usually metals like gold or copper, they work very nicely. But we are also looking at new materials, even 2D materials, because they can, in principle, bring the two wafers even closer. Though ideally, you want a zero gap between your photonics and electronics.
Okay. Okay. Thank you.
Okay. More questions? Okay, please.
I was wondering, I'm not from this field, but I've heard a lot about lithium niobate for nanophotonics. So how, I mean, of course, it's very far from being at the point where indium phosphide or semiconductors are, but do you think there's actually a real potential for lithium niobate to get where all these amazing semiconductor circuits are?
Yeah, I think it hits one of the points. I think the future is to combine different material systems to really benefit from each of them. For the lithium niobate, the major selling point is the electro-optic effect. It's extremely pure electro-optic effect, so you can get a low loss. I think it's very nice material for optical modulation and also some nonlinear processes, right? But it cannot generate light, or there are some work also on integrating lithium niobate with silicon and also with indium phosphide. That's, I would say, the best way to move.
More questions? Yeah, please.
Oh, thanks for the talk. And I was always wondering about the heat. And does the photonics really susceptible for the heat, while the electronics is not? Is it true or not? The heat management in the photonics circuits, is it really important, or you think it is overcome?
Yeah, it's as important as heat to photonics and to electronics, and both in the performance degrades when inside them the core when it heats up. So it's common for any kind of photonic electronic system. You need to have a proper thermal management plan for your system. Yeah.
Okay, thanks.
More questions? If no more questions, I have one small short.
One.
Okay, sorry. Sorry. Yeah.
So my question is about, in general, about photonic computing. How do you see the future of computing being influenced by photonic computers?
Yeah, it's there are a lot of debates on it. I have to say, in terms of computing is a very broad topic. So in terms of logic or digital computing, there's no way photonics can do that, because all the photonics things, they are analog, right? But then again, photonics can be very powerful if you find applications that people can use analog processors, maybe next to a digital one, or very task-specific analog computing. Then I think photonics can play an important role. Like I said, the reason is photonics is much lower loss when transporting signals than electronics. And the photonics, you can stack them by wavelength, by polarization, which electrons don't. So yeah, I think there's a niche angle that the photonic computing can have a future. Yeah.
Thank you.
Okay. So my question would be about the patience. How long it takes to prepare 6 inches chip?
You mean to fabricate these?
Yeah, yeah.
PhD level, a year.
Yeah.
Yes.
Yeah.
Because
So,
we are.
so be patient, young
Yes,
scientists. 1 year in order to prepare such large integrated chip. Okay. Thank you very much again. Yeah. And yeah. And I would like to invite our colleague, Kristijonas Visbaras, brother of various processes and phenomena, brother semiconductors, brother sensing, brother defense even. So Kristijonas, now is yours. Thank you.
Thank you. Good afternoon, everyone. It is my pleasure to be here. I will now briefly talk about Brolis companies and the job opportunities or the activity opportunities that we propose and what we have. So to start with, Brolis is a group of companies that is specializing from defense to sensing activities. The beginning of Brolis was started by myself and my 2 other brothers. So my background is physics, semiconductor physics. I started in Vilnius University 20 years ago. I was also participating in organizing Open Readings conference. So just like you are here sitting today. Then the journey took to Sweden, Germany, and finally we ended back in Lithuania, establishing a high-tech company. We started from semiconductor components manufacturing and then gradually shifted to defense. And then the other activities, we're located north of Vilnius. In the picture here is just one of our facilities. There's another one 300 meters away, and I believe we will be expanding in the near future elsewhere as well. So we are active in defense, agriculture, and industrial applications as of today. So I'll start with the defense activities, which are maybe most known in Lithuania locally and globally. So Brolis today is a well-known electro-optic system manufacturer in the defense sector of NATO and NATO partner countries. We have delivered over, I think that's a bit outdated slides, over 60,000 systems globally. Our revenues last year were around 18 million euros. This year we expect to top 50 million euros. So we're a very rapidly growing company with over 70 plus employees just in the defense company, and our systems are used and utilized in more than 35 countries worldwide. So in order to skip talks, I will just go through a video where you will see the applications and the systems we manufacture and where we manufacture, so you can have a better understanding.
It's all about the advantage. And this is where the advantage is created. In our state-of-the-art facility, we design and produce lasers, night vision, thermal, and SWIR electro-optical systems. Every single one has a technological edge, one that makes a real difference in real-life situations. That's what made us licensed military system developers, and why our systems are extensively used and valued across the NATO alliance. Not only are they precise, but they are also battle-proof. Created by brothers, for brothers in arms.
So a short video just to save my and yours time. So just as mentioned before, we have a global footprint. You can see our sales structure by markets in this graph. So really a global supplier. and supplying in large numbers, and not only various special units and so on, but also green armies of the top countries within the NATO and the allied map of the world. So starting from, of course, Lithuanian armed forces to Belgian army, Spanish, Finnish, Ukrainian army, and so on and so forth. Due to the times that we are living in, we are also very active in Ukraine. On the Ukrainian side, of course, we are a licensed supplier to Ukraine. We are supplying directly, indirectly, and by all means possible. We are part of that war that is happening there, and we're helping the Ukrainians as much as we can. So this is just a set of countries that we are serving with our certain flagship products. And yeah, if you want to be part of the defense, that global journey of us, apply, look for open positions, what we have, and we will always invite you for an interview. Now I would like to jump from guns to roses, to our sensing applications, to Brolis agriculture applications, where we utilize our, I would dare to say, deep tech solutions that have over 35 patents globally around them, where we start from really semiconductor components, so semiconductor optical amplifier that we grow in-house from gallium antimonide-based materials that we integrate into very complex laser cavity that utilizes ultra-widely swept laser-based sensors that today we are actually very successfully commercializing in the field of agriculture. So referring to the talk that was just before, I would like to remark that I have deep respect for the professor and to all the people who are involved in the photonic integrated circuits world. We have been active and we are still active in that field for over last decade. It's still immature for the final industrial applications, but the potential and the depth of the technology is remarkable. So today we are utilizing non-photonic integrated solutions in our commercial products, but we also have prototypes that are based on integrated photonic integrated circuits as well. So about the milk sensor and the agriculture applications, I'll just try to launch the slide here. And you will excuse me. There you go.
Brolis inline milk analyzer is like a mini laboratory on your dairy farm that measures milk composition for each cow during every milking. Our system doesn't require additional reagents or manually taken milk samples. It's all automated, even the cleaning procedure. While milk flows through the tube, multiple sensors continuously measure fat, protein, lactose, and other parameters. This portable next-generation infrared laser sensor is the reason why we can be precise and accessible to almost every dairy farm. The Brolis analyzer is designed for conventional or robotic milking systems. Data is gathered and processed in real time using Brolis herdline software, which gives you vital information about the health, productivity, and profitability of your dairy herd. Contact us today to arrange an initial consultation with one of our specialists. Brolis Herdline. Focus on the herd data you need.
So maybe that's a bit radically different field from the defense, but nevertheless, from the scientific perspective and the depth of the technology and the science around it, this is a very, very advanced product. And I mean, I will not emphasize commercially. I mean, it's also a big deal if you can, how to say, look at the agricultural market. So take Denmark, for example, you have 5 million people and 20 million pigs. So that shows you the market is much bigger on the agricultural side if you want to do some monetization in there. But sensor like this that we are now applying in the milking lines and in the field of dairy farm It is also absolutely functional with other biofluids because it totally doesn't matter whether you're sensing milk, whether you're sensing blood, saliva, or anything else. You can get that same data with our widely swept laser-based spectrometer. We're able to tell apart and sense different proteins, different fats, different other biomarkers such as lactose, glucose, different sugars, caseins, and so on and so forth. Collecting that data, not only we can get very precise concentrations of those, but we can also, utilizing the data science around it and the veterinary knowledge around it, or the medical knowledge, if you give it to me, around it, we can tell a lot about the herd health or the individual health and so on, make models that allow the, in this case, the farmer or someone else to adjust the feeding, the treatment of the cows and making the farms more efficient, getting economically better, but this also applies to, in the future, to the human life as well. So if you can do early diagnosis, if you can monitor in real time things, you can tell a lot, you can prevent a lot of sicknesses, you can introduce healthier lifestyle, you can save a lot of money, you can also, as a business, earn a lot of money. So just to showcase that this technology is one of a kind and unique, so early this year, Brolis has been ICAR validated. ICAR is an international organization similar to FDA or CE, just for the in sector of agriculture, so dairy farm, is that it validates inline analyzer as a laboratory accurate device. So this is world's first such device that has been validated. No solution has existed before. So we are the trailblazing this market, and we introduced the first solution in here. And this is actually creating kind of a quite a revolution in the dairy farming business. We are also as this sensing company growing with that. So this year marks our first serious sales, and then we see to become quite a solid company in the next 3 years. So this company unites not only physicists, but veterinary, mathematics, biology, mechanics, electronics, and so on and so forth. So plurality of specialists that we're looking for, plurality of deep scientific and talented people around it. So if you are interested in working of something like really cutting edge technology or getting in touch with some very precise processes and again, be part of a global journey, so keep your eyes open, look at our job adverts. We are constantly looking for people, for talented, hardworking people, and make sure you contact us. So we will definitely interview and welcome you aboard. Thank you.